now we're going to analyze the same system we just looked at. So let's go back and just remind ourselves of the system. So we looked at M1 rolling without slipping. M2 is just rotating. And M3, of course, is translating. So we're rolling and translating, just rotating and just translating. But now we're going to analyze and think about how we would solve this system based on looking at Newton's second law for both translation and rotation, namely sum of the forces and sum of the torques. Well, to do that, we need to do force diagrams for all three of the objects in this problem. And let's start with the easiest one. Let's start over here with M3. So M3 has gravity pulling down and tension 2 pulling up. Remember, tensions pull, never push, and that does not change. The rotating pulley disc in the center is actually the hardest of them. So let's go over here to 1 and see what's going on with mass 1 that's rolling without slipping. Well, I like to always get gravity in first because I'm sure I got that right. M1G down, the force normal, up, tensions pull, never push. So we have T1 going off to the right. Let me get a T1 in here, going off to the right. So tensions pull, never push. That's like the rolling pin pulling forward. And of course we have friction to the left. So left, right, up, down, we're fine. Now let's look at the rotating disc in the center. Well, gravity is gravity, so I like to get gravity in first because I know I got that right. So just looking at the rotating wheel, gravity pulls down, and I know I have strings in the problem, so we'll get to the green, put these in last in a moment. We have the strings in the problem, so we have the, let me get this in here, we have the tension T2 pulling down on the wheel, and please get these extra little comments into your notes. The fact that tension T1 and tension T2 are now different because we no longer have an ideal pulley where it's not really a pulley, it's just a frictionless cylinder where the rope slides over the top of it. Now we must acknowledge that T2 is different than T1 and greater than T1 because we know the wheel is rotating clockwise as M3 falls down. So I realize I have it pre-annotated for you, but we have tension T1, mg, and T2 put in. Now let's think about what the pin is doing. Well, I drew them in as green because they are normal forces, and the reason I have to put these in last is, look, I have two down forces here. Well, that pulley is not moving up or down, so we need a force acting up from the pin. And we only have T1 to the left, so that means we also need a force from the pin going to the right. So you really only know the directions here after you've put in all the other forces. If our force diagrams are done thoroughly, completely, correctly, then writing down the F equals ma and some of the torque equations really are not that difficult. Let's look first at M1. So we can start over here now. It doesn't matter if our force diagram is done. Sum of the forces in the x direction equals mass 1 times acceleration in the x direction. And oh, I almost left off one of the most important. Please make sure you highlight or circle or put stars or all three next to this. Since all of the v's are the same, and we talked about that in our last lesson, that the tangential velocities on the rim of the wheels, the linear motion of the M1 and linear motion of M3 all are the same. The linear accelerations will also have to be the same, so I can drop the subscripts on the accelerations. Okay, so M1 times A. Here we have tension. Oops, I need a T1 in there. Please make sure you put, it's not T, it's T1 minus force of friction equals mass 1 times acceleration. And of course, friction is mu times the force normal, which is M1G. In the y direction, notice force normal up and mg down have to equal each other, so that's a very simple force normal minus mg equals 0. And let's take a look at the sum of the torques. The first thing we must acknowledge is that our pivot point is given to us to use the center of the cylinders as the point about which we're going to calculate the torques. So our pivot point is here, and we're going to do R, which is R1, cross F. The force normal, tension 1, and mg all act through the pivot point, so they won't contribute to the torque. Only the friction allows the torque to be calculated. So let's do this. Torque, R1 cross F, force of friction, sine of 90 degrees. I1 is given by 1/2 mr squared. It's a solid disk. A equals alpha r, right? So that's our A equals alpha r. So alpha equals A on R. We drop the subscript on the A. We have R1. It is rotating clockwise. So that is a thumb into the paper, right? So disk 1, let me erase this and clean this up a little bit. Disk 1, right, is rotating clockwise, right? So that's a thumb into the paper rotation. That's a negative. So we have a negative. Actually, I should have that negative in here as well. Let me get that in here. So we have a negative here because alpha is going to be negative, and we have a negative here from our R cross F, thumb into the paper, so we lose both of those negatives. And when we cancel out our R1s, right, so you can see here that we have an R1 in R cross F, we have R1s in 1/2 mr squared, and an R1 down here. We lose all of the R1s, so the frictional force equals 1/2 M1A, force normal minus mg equals 0, tension 1 minus friction equals ma, so we have 3 equations. Now, we're not going to plug in numbers on this page. We have a lot going on. But basically, we're going to collect all of these equations and all these unknowns and hope that we have enough to problem solve the problem. Now, let me erase here in the middle so we can kind of get a better feel for what's going on. Sum of the forces in the x direction equals 0 for the pulley because it's only rotating, it's not translating. So that means the pin force in the x direction to the right has to equal T1 to the left. In the y direction, we have the 2 downs have to equal the 1 up, and that's what we have. The 2 down have to equal the force of the pin up. And we do the same thing with our torque here, but now we have 2 competing torques. T2 is trying to rotate the wheel in the clockwise sense. That's why we have the negative here. T1 is trying to rotate it in the counterclockwise sense, so that's why this is positive. And remember we said T2 has to be bigger than T1. Please make sure you get that into your notes. Let me just go back and remind you. All right, T2 must be bigger than T1. And there's our positive and negative. It is still that negative that I left off of the M1 motion is still there, so that's negative. So our positives and negatives are correct. We still cancel out. Our R2s come out. So if you look, we lose all of these R2s cancel, and we have T1 minus T2 is negative 1/2 M2 times acceleration. And of course, we have our other equations. So now I have 6 equations to work with. And our last equation to work with is simply that there, of course, are no x forces at all, no x consideration for M3. The force M3 equals mass times acceleration. We have T2 up minus m3 down. And notice the most important thing about mass 3 is to make sure you get the negative in for the acceleration, because m3g is definitely winning out over t2 because the mass will go down. So there we have our 1, 2, 3, 4, 5, 6, 7 equations to work with, and that is it. That's all we have to work with. So we better hope that we're given enough unknowns to be able to plug in, and if we have to, we solve 7 equations and 7 unknowns, and we can put that into our calculator and row reduce echelon format. But you can see this is definitely a more complicated approach, more to it, but we have no choice. If we have to calculate the forces, the tensions, we can't use the energy approach. Remember, in the energy approach, we didn't use any forces. So let me erase this and clean up all my additional inks, except for the tension one here and the negative here, right? So we have the negative there. All right, so let me leave this for you. You can pause the screen if you wish and make sure you have all your annotations down there, but hopefully the explanation was helpful in terms of how to analyze this combined motion using forces and torques.